stack, front end, back end, project management, DevOps. And I've been with them for 8 years. And for the last 2 years, I've been consulting as the technical lead on the store and menu team at Yum Brands. And while there, I was developing the API and data model used to author menu contents and publish those menu contents to different stores. And for the last year of that, we've used Temporal via the TypeScript API, TypeScript SDK to publish our menus. And this talk will have some TypeScript examples in it, and there's a TypeScript example project, but the terminology or the concepts that we discuss are going to be applicable to any SDK. Anyhow, it was during this time at Yum Brands developing their menu system that we had this need to coordinate our workflows. And let's talk about that scenario a little bit. So this scenario is something like this. Let's say that Pizza Hut wants to introduce a new promotional bundle nationwide. They're introducing, in this case, the Barbenheimer box. And yeah, they're going to be introducing this nationwide. They want to ship that to all their stores, this new bundle. And they assign it to a menu, and then they make a request to publish that menu down to the stores that are using that menu. And as a result of that request, there's a temporal workflow that gets kicked off in the background that processes the menu contents, generates that menu, and then ultimately uploads it to the different systems in store. However, just as this is going on, as the Barbenheimer publish is happening, Store X is also being selected to receive another new product. The Doritos Pizza Locos Pizza. It's just one giant tortilla chip that's a pizza. And yeah, Store X is going to be seeing if this is a popular product. And so an admin user has gone and published this to Store X as well, at the same time that the Barbenheimer publish is ongoing. So there's a temporal workflow that's kicked off, and that means that we have these two temporal workflows running at the same time. And it's entirely possible that the workflow we kicked off second ends up publishing its menu first and getting its menu overwritten by the first workflow execution. And that's something that our users wouldn't expect. Our users expect that the second publish takes precedence, but we aren't doing anything to guarantee that right now. So we have to do some sort of coordination to make sure that guarantee is in there. When you publish to a given store, you're going to publish in the order that those drops were kicked off in. So to sum up what led us to this use case, we're releasing to hundreds of stores at a time. The users may end up making these back-to-back publishes to a store. We need to avoid making those back-to-back publish or having those back-to-back publishes race to upload their workflows. We need to make sure one completes before the other. And there's only a portion of our publishing process that needs this mutually exclusive behavior. When we're publishing to 10 stores, we can get that base menu ready and get it ready to send to all 10 stores. It's only when we get ready to upload it to one store that we have to put that lock in place. And that's because we're communicating with multiple systems in store that need to be synchronized. When we're talking to those in-store systems, they're communicating with each other, there's validations happening, and we need to make sure that all those in-store systems have the same data at the same time. So we can't just run both in-store at the same time. So we have this need to prevent these racing workflows, and there's a couple ways that you could approach this problem if you ended up having racing workflows to deal with. The easiest being that you can just reject the second workflow. If you can do this, if this is good for your use case, it's the easy way to resolve this. Just let the first workflow finish, return an error saying you can't kick off the second workflow yet. This wasn't a great option for our case because the users in our system actually want these workflows to complete. Like, we don't want to give them an error saying, well, you can't upload right now. We would like to enqueue it so that they don't have to like sit around and just like press the button to see when they're going to actually get the opportunity to enqueue their job. Another good option, if you're able to swing it with your use case, is just to supersede the first request. If you know that the second publish needs to take precedence, just cancel the first publish. It's an ongoing workflow. You can cancel it, and from there, you can just proceed with the second workflow. Again, talking to your users in this case, this wasn't a behavior that they liked because some user out there asked this store to get this menu. We don't want to just abandon some work that a human being has actually asked us to complete, if only so that they have like a point to roll back to. Like if this Doritos pizza doesn't work out and they just want to roll back to the national menu, it's nice if that's in their history to roll back to and we don't have to do another full publish process. Another solution, if you can handle it, it's a little bit more technically complicated, is to make your workflows both finish, but make them finish in such a way that the second workflow, even if it completes first, will still take precedence. So some way of the lagging workflow knowing it's running out of order and to not activate its menu. It would complete its menu upload process, but it wouldn't actually bring up the store to use that menu. This is a little bit more complicated, so we didn't end up going with this approach just because you have to have a process that can accommodate it, and you can potentially have some race conditions when you're trying to do this approach. Another approach, if you're new to Temporal and you're not really familiar with the primitives yet that are available to you, you might think, oh, I have this thing called a task queue. I want these things to happen in order. I can just put them all in the same task queue. They're going to execute in order. And that's true in very limited cases if you only have a single worker and you've limited your worker parallelism so that you're only ever executing a single activity at a time. But this is limiting your parallelism. It's really tying your hands with how you can scale your business process. So it's not a very good solution. It's kind of not using Temporal the way it's intended, but we actually have had clients come to us and say, oh, we got these tasks used. We can use this for coordination and serial execution. And we tried to lead them away from that. And lastly, that leaves us with the option of just executing your workflow serially by using some workflow to coordinate which one will execute first. So we're going to talk about this for the bulk of the presentation. So coordinating access to a resource like this is a fundamental computer science problem. I think most of us have heard about how to solve this. There's synchronization patterns out there, and the one that's appropriate for this case is a mutex, a mutually exclusive lock. Workflow synchronization, these mutexes aren't shipped as part of the Temporal API. The pattern is something that you can implement using the primitives that Temporal gives you. And that gives you a little bit of flexibility in how you can implement this mutex and this sort of serialized behavior. So we're going to talk through two approaches to that in this talk. The first I called queued execution, and the second I refer to as a queued signal. So let's take a look at that first one. This implementation has two workflows. You have a requesting workflow and a queuing workflow for each store. And the requesting workflow signals to the queue workflow that there is a new publish for it to perform. And then that queuing workflow, if there's nothing in the queue, once that request that came in is at the front of the queue, it'll do the publish activities for that store and then signal back that it's complete to the requester. This is a nice, simple, straightforward approach. It's the first approach we took to this problem at Yum. And it's a good approach that solves it in a nice, efficient, and minimal way. It's kind of modeling your workflows after your entities, kind of using the actor model. But we eventually ended up moving away from this, and we'll talk about that a little bit. The other approach we have is not quite as minimal. It uses a third workflow, and that third workflow is a lock workflow, and that is what does the cross-workflow coordination in this circumstance. The top workflow starts a child workflow, and that starts a child workflow for each store, and that child workflow is where that business logic to actually do the menu generation and deployment to the store is going to be. The lock workflow is responsible only for sending the signals to the child workflow to let it know when it's turn to execute. So with these two workflows kind of broadly introduced, I'll take a deeper dive on that first approach. The first approach is shown here in a little bit more detail. We use a signal with start to pass a append publish message to the store publishing workflow. And then we perform those activities and then use a signal back to the parent workflow, to the calling workflow. So we'll jump into some code here for what that top level workflow looks like. That workflow takes a menu ID, sets up a set of stores that are using that menu, and then signals to all of those stores that it has a new menu that it should be adding to its queue for publishing. We set up a handler to receive messages back from those queue workflows, and we wait until all of our expected stores have sent their signals back to us. And then at the end of the process, we delete our temporary menu that we've been using, and publishing is complete. But we'll go one level deeper. We'll go into the signaled workflow here, the queued workflow. And this queued workflow takes a store and an initial list of jobs. Because it's a long-running workflow, it may have been started by exceeding its max workflow history, and then any jobs that were in its queue were passed off to a new job. That's kind of a pattern within Temporal when you're using continue as new. Once you hit your workflow history max, you'll pass any work that needs to be completed to the next workflow that you start with continue as new. But just kind of starting from the top here, it sets a handler up to receive new publish requests, loops until its workflow history has either exceeded that point, and if it hasn't, it will wait for a message to come in up to some sort of like max limit. We don't have these workflows living forever. If people are doing publishes infrequently for a store, we actually don't need to keep these around. So we have like a couple hour max workflow idle time here that if these workflows are not needed, they shut themselves down. After that job comes through, it actually perform the workflow publishing activities in this try catch. And then it'll finally send the completion signal whether or not it succeeds or fails. We want to let that parent job know that it's completed one way or another. Yeah, so and then this workflow continues to run forever, waiting for any other jobs to come in, or until its max history or max idle time are reached. So now that we've seen how this works a little bit, let's talk about why we chose this approach. And it's less code. There's one less workflow involved. And one less workflow means fewer workflow executions involved. So you actually have a more efficient workflow here. You don't have the lock involved, so you're just sending fewer signals and actions back and forth. So there's some lower cost. And you're modeling your instances after the entities they represent, which is just kind of a good practice within Temporal. I'm sure we've heard it a lot this conference. So yeah, like I said earlier, this works. Our Barbenheimer menu and our Pizza Hut Doritos pizza no longer conflict. They'll be published in order. However, in our case, this started to present a few difficulties, mostly around the signal back from this process. This store publishing process has a bunch of unrecoverable or like non-retriable failure states because we're publishing to these stores and we're publishing to multiple systems in these stores. If the kiosk is down in store, like their kiosk system isn't operable, but our deployment system wants to update that kiosk, it might fail. If their internet's down, there's just a multitude of reasons that we can't really account for why a publisher would not be able to complete. So this signal that we had to handle that. We needed to inform our parent workflow that some sort of failure had occurred because we couldn't just kill the queue. The queue couldn't be allowed to die. It has other publishes in the queue that it needs to complete. So we have to keep that queue workflow alive, and we can't just throw an exception. Instead, we have to catch the exception and send it back to the aggregating parent workflow here via that signal. So that signal now no longer kind of has the temporal benefit of only worrying about our like happy path. We're now having to encode all of the different failure states that could occur in that queue into the signal and then aggregate them in the parent. And the handling around that just meant that like we were losing some of that benefit of Temporal of only thinking about like the happy path as much as possible. And because we are sending all of these failure cases from our child workflows back to this aggregator, we can potentially exceed the max workflow size, the context size that's available for a workflow. If you're giving like detailed explanations of the different failures that could occur during the store publish activities, and you're publishing to several hundred stores, you want to communicate these different failures to the user somehow, so you have to get details back about them and aggregate them somewhere. And so you have to send them back to the parent workflow so that they're accessible somewhere, or you'd have to save them to some outside persistence of some sort. So just like how do we pass these like failure messages around without exceeding the max workflow size? And then it also was a little bit more difficult to debug this because that queue workflow can't be allowed to fail. You have to keep it alive. when the business logic that's in that workflow has a non-recoverable bug in it, when we've made a flaw in that workflow logic, we don't just see like a failing workflow in Temporal. What we see is some sort of error reported to this parent workflow. And then we have to say, okay, this parent workflow has an error in it. That maps to some queue. And then some portion of that queue's history is where our error actually occurred. So like our error isn't encapsulated by a failing workflow anymore. We have to find out that our error happened during aggregation. And then a developer has to find the appropriate queue and then isolate the portion of the history that was responsible for generating that error. It's not impossible by any stretch, but it just adds some more friction to the process of debugging when you have to look into this queue history to find that. So for these reasons, we started looking at some potential alternatives. And what we landed on was the signaled approach. Nope. I have to click on, here we go. There we go. The signaled approach. And in this signaled approach, the business logic is running in this child workflow that we're calling into with execute child. So that gives us kind of a promise wrapped around the execution of this child workflow. We will get a response signal back to our parent workflow without having to set up that signal object. Like it'll just be a normal return value or an exception. So now instead of having that signal where we have to model all of this complexity and all these potential non-recoverable failures, we can just throw an exception and we kind of get back to that happy path. The only thing we have to handle is exceptions at the top level where we see these child fail, and we can just say, oh, this workflow failed. To find out the details about that, you can now actually query into the temporal workflow history and visibility and look at what state that workflow is in through the API very easily. So this approach is heavier weight, but because it encapsulates our business logic in that child workflow, we have a lot easier response handling. So let's get into the code for this approach. And starting at the top level workflow, it just takes a menu ID, finds all the stores using that menu, starts the publish workflows, kicks off those children, executes the children, and then just uses a promise, waits for all those children to complete, and cleans up the temporary workflow. There's no signaling inside of here anymore. So then the child workflow that is run from here, that actually does the menu publishing, sets up a handler to receive the signal from the lock. It then sends a signal to the lock that it would like to execute, and then waits for that signal to come back. That's that condition there. And so then once that signal is received from the lock, it can execute the store business logic and then just signal back to the lock that it's finished. And then from here, it can just return or throw an error up to the parent without having to model that as a signal. And then at the bottom level, this is the actual locking workflow, and it looks a lot like the earlier queuing workflow, just a little bit more generic. Instead of after we take a request off of the queue, instead of doing the actual business logic, what we do is we generate a signal that we then send back to the caller saying, this is your signal to tell us when you're done. So we send a signal back to the caller, they can do the business logic, and then they signal us back that they've completed. So now that we've seen both approaches, let's talk a little bit about why we ended up choosing the more complicated one. The advantages of this approach for us were pretty substantial. Like first is that I've talked about it, it made our response handling a little bit easier. We don't have to wrap everything inside of a signal. It makes developing on that a little bit easier. We have clearer workflow hierarchy and history. So something we serve through our API to our users is if a certain store has a failure, you can query our API and find out as part of publish number 10, why did store X fail? So this is actually an entity in our API, and now instead of having to pick that out of some aggregate that we're building at the parent level, we actually have a workflow that encapsulates that. So if you want to find out the failure, we can actually call the Temporal API and just pick the failure out of the temporal workflow history. It's a lot easier than having to aggregate it or cut it out of some segment of the shared queue history. Sorry. This is also, yeah, I've talked a little bit about how having that history makes our debugging a little bit easier, because that history is now no longer shared. If something fails, it's encapsulated. And then this also gives you a reusable locking workflow. Like if you have different circumstances in your org where you're going to have this sort of synchronization pattern, this is a workflow that you can reuse anywhere. It doesn't have any business logic in it. And there's just some use to not having to couple your business logic or rewrite this coordination. And it kind of ties in my last point is that it's trivial with this generic approach to coordinate multiple locks. Like let's say we had some other service, some other workflow that synchronized the state of 2 stores. So to do that, I would have to theoretically lock both stores before I start the synchronization. And using the first approach, you have 1 queue. There's no way that you could really represent 2 resources with the first approach. You've coupled 1 queue to your business logic, and trying to add a second queue and trying to do a second lock just really isn't possible in the first approach. Whereas this approach, you just communicate with an extra workflow. So these are the theoretical improvements that we kind of assessed, and let's talk about how it actually bore out in practice. Practically, like we did end up achieving that simplified signaling and error handling that I've been talking about. The shallower learning curve of kind of separating our business logic from the coordination logic. For developers that are new to Temporal or who are like generally just kind of on our team to work on the business logic, they're not really Temporal experts. Now when they go to make edits to that business logic, it's encapsulated in a workflow that doesn't have like the signaling, the coordination, the max workflow length, just kind of like a little bit more cognitive overhead for developers who aren't super up with their Temporal. Yeah, and just abstracting the business logic had made that a little bit easier as well. And it's a little bit more similar to a typical thread mutex if you're someone who has used those in the past. For us, this actually ended up producing a negligible increase in overhead and costs. I mentioned earlier that this is a little bit more expensive approach because you have a third workflow involved. There's just more signals. But in our case, like let's say like we saw that there was a difference in 3 actions. You send 3 additional signals when you're talking to this extra workflow. And for our level of use for the menu team, this was negligible. For example, like we could have done 1,000 publishes, like let's say 1,000, that's like 3 times a day for a year, let's say, of 2,000 stores, which was every KFC in the US. We could republish every KFC in the US 3 times a day for a year, and it would result in $150 of additional costs. So for our use case, because we only have several million of these locks per year, really, it wasn't a major concern, the overhead or the cost associated with this. So yeah, I have some thoughts to close out with. I would recommend some consideration before implementing the queued execution pattern. It's nice because you have that kind of actor model, but just like I said, there's like some complexity around that when you're handling signals. So my suggestion would be that you would use queued executions if your case doesn't really need to return a complex value or likely any value. Like if you can do all the retries you need and you know this is going to be a stable process and you don't really have to do a lot of like failure or like unhappy path handling in that shared workflow, then I would say it's a good fit for the actor model. If you don't benefit from having that structured parent-child relationship in the workflow history like we do, we use that structured parent-child relationship to actually power the responses from our API about that status. So we benefit from it and just the debugging benefits. And then if you're someone who's really using Temporal heavily, if you're running your workflows and would need these locks to run tens of millions of times a year, hundreds of millions of times a year, then certainly the more efficient approach makes sense for you just for the cost savings and efficiency. But if you're unsure, if you don't think you're going to hit that scale, I personally would suggest recommending reaching for the queued signal approach. It's a little bit more composable and it's a little bit more familiar to developers who have worked in other threading environments. Yeah, so thanks for attending my talk. And thank you for everybody who helped me edit this slide deck. It's been a lot of help.